Assalamualaikum and very good morning to all the panels MTE 2023. My name is Associate Professor Dr. Muhammad Asrimat 3D from Solar Energy Research Institute, University Kebangsaan Malaysia. Okay, today I'm going to present about the finding in our lab regarding the perovskite solar cell, which is the new type solar cell, third generation solar cell to replacing silicon solar cell. Okay, this topic is a very interesting topic in Malaysia, and now it's become more interesting since the government of Malaysia introduced for the more green energy, which is replace the fossil fuel. Yeah, so this is one of the finding we are looking to introduce the new type of the solar cell, which is can be used in the to generate the electricity. Okay, now our topic is a novel microcyclic dibenzotetraaza annually as an electron transport layer for boosting the stability of perovskite solar cell. Because why we choose this topic, we know one of the main issue for the perovskite solar cell is a stability issue. So we try to counter this issue, and then we come out this idea and using this material dibenzotetraaza annually. As we know, after this I will mention about DTBAA, yeah, to increase the stability of the perovskite solar cell. Okay, so as we know, yeah, perovskite solar cell, as we mentioned before, the device which is organic inorganic material, yeah, because we are using perovskite structure material to generate electricity, yeah. So as I mentioned, the main issue in the perovskite solar cell is stability. So by using this material, what is interesting in this material, the TBAA, this is a hydrophobic material. When you're using hydrophobic material, that means they prevent from the water to absorb by the cell. When the water is not absorbed by the cell, they will improve the stability of the material. Okay, so we explain the finding later. Okay, now we go for the methodology. This material, we are synthesis the material. Yeah, we are synthesis the materials, and at the end, what we got 75 yield. That means only 25% will be is not be used. 75% is the product for the material itself. Yeah, and after we got that, we fabricate the perovskite solar cell from the cutting of the glass up to encapsulation. All we done in our lab. Yeah, all we done in our lab. The structure of the material, you can see we are using FTO as a substrate, the device. Yeah. We are using like TiO2 for electron transport layer, or the material, the DTBAA, perovskite, yeah, for the active materials, and spirometer for the whole transport material, and then for silver as a contact. So the product is on the side of the device structure. Yeah, this is the product what we are producing. Still a small scale, yeah, still a small scale, but there's still more room to be improved. Okay, what we can see here, we want to make sure that we got the NH peak for the TBAA, yeah. So we measure the NMR, and then we prove we got it, yeah. So after that we measure the other also, yeah, the other also, but we not include here. Because this is a limited space, yeah, and then also because of we are filing for the patent for this material and for the perovskite solar cell, so we not include all in this structure. So we straightforward go to the performance of the device. Even the slightly what we got to make a comparison, we make a two device. One is based on TiO2 as electron transport layer, and another one we make a DTBAA as an electron transport layer. But the rest is similar. It's like the structure we mentioned before. So what we got here, yeah, slightly lower the efficiency, the JSC, the fill factor compared to TiO2 from the DTBAA. But this is what we our expect, because the material usually the TiO2 is most people have been used and been studied, yeah. But this is the material is still new, yeah. But what is the interesting? We go for the stability, yeah. After we measure the stability up to 3 months, what do we achieve? Yeah, for normal TiO2, what we are using, they will reduce to 20. They will reduce about 80%. It's become only 20% still working for the device. But when we are using our DTBAA, the stability still maintained up to 87%. Yeah, 87% after 3 months, which is very impressive result. Yeah, very impressive. That's why we are patenting this product. And then as a conclusion, what you can say, like the DTBAA, which is that we are synthesis, can be used to replace the TiO2 for the perovskite solar cell. Yeah, and then what made the stability is about 87. The stability about 87%, which is the most stable perovskite solar cell produced in Malaysia until now, as far as what I know. So this product also under its filing patent, yeah, and then this is what I say. This is the future for the perovskite solar cell, yeah, new later on. And then the other interesting is we just secure some funding, SRF funding from the MOSTI. So we're going to use these materials, all the structure, to scale up and to boost the market for the perovskite solar cell in Malaysia. This is the first, and I hope this to be the new benchmark of the perovskite solar cell. Thank you very much.